I'm doing a patch and it's going to be a rectangular patch. Now patches can come in different shapes. You can make it a circle, you can make it an oval. There's different ways to do it. The rectangular one is the most straightforward one. What we're going to need is, again, if I were to Google patch antenna with patch antenna, it's going to look something along the lines of this, where you have the patch, you have some dielectric substrate, and then you have a ground plane. Okay, so we're going to need to make these three separate things on top of each other. Now, in this case, it's being fed by this strip over here. We're not going to do that. We're going to feed it through a probe. So let me see if there's an example of that, where there's a coax that's drilling like exactly like right here, where instead of a strip feeding it, we just have a rectangular patch and you have the coax cable going into it. Now, this is going to be very nice for our CubeSat, because obviously we're going to have the antenna on the side of the CubeSat, and we want the signal to come from the inside of the CubeSat. Obviously, the radio will be stored inside the CubeSat box. So this will act as a really nice interface. So perhaps you could use like this SMA connector as a means of connecting your patch antenna to the radio inside your CubeSat. That's what we're going to do. So first I'm going to start with a substrate, and then I'm going to add the ground plane, and then I'm going to add the patch. And then what I'm going to do is I'm going to drill a hole to allow for the coax to go in. I'm going to draw this coax feed, and this is going to be basically our wave port feed. And then I'm going to add this metal pin that's basically connecting my coax signal into the patch antenna. Okay, so it's a quick outline of what we're going to do. So for the 2.4 GHz antenna, you will use like an online calculator, or you want to use antennatheory.com to calculate dimensions. You guys already calculated dimensions last assignment, so you want to just go ahead and implement them. So this is a rectangle. I don't want a rectangle. I want a box. So I'm going to click here on the box, and I'm going to just draw like randomly and give it some arbitrary height. And I'm going to adjust the dimensions in a second, but this is going to be my substrate. So I'm going to change the name of this to substrate. And instead of vacuum, I'm going to actually give it a material. So like there's many different kinds of substrates that are used. A very common one is like this Rogers RT Droid. It's a very industry standard. And again, it's just dielectric. And you can Google that material. And here ANSYS already has the values for it, so we don't need to calculate it. But if you want to go for your own dimensions, when you go figure out your calculator, you can assume that this is the relative permittivity for this material. Okay, you could use a different material as long as you indicate in the assignment that you chose to use a different material. And we're going to keep that as green. We're going to make it a little transparent so we see what's going on around it. Okay, so right now it's just some arbitrary box. I'm going to give it my pre-calculated dimensions, which are -5, -4.5. And I'm going to have it with baseline at 0. I'm going to give the X size 10 centimeters and the Y size 9 centimeters. And then for the Z, which is the height, I'm going to give it 0.32. Okay, so this is what it should look like. So it is a rectangle, basically. So I'm going to basically take that and I'm going to draw a ground plane right beneath it. Okay, so this takes care of my substrate part with its thickness and whatnot. I know when I'm viewing it, it's like acting weird, but it's there, I promise. So now I'm going to draw a rectangle.
Can I see the dimensions to that real quick?
Yeah, so dimensions are right here. So this is the position, -5, -4.50. The X size is 10. The Y size is 9. The Z size is 0.32. Okay.
How did you get to that window?
So when you draw the box, it shows up. So if you pick a random box and just let it be created, you click on the create box, and that gives you the dimensions. Okay. Now, if you want to change the name, you go to the box itself. Okay. This is how you change the name, and you change the material. Okay. All right. So I'm going to get rid of this box. Nope. All right, so now that we have a substrate, I'm gonna create a ground plane. Now, a ground plane obviously is just a sheet. It's a rect. So we're not gonna use a box. We're gonna use a rectangle, and we're gonna put it right beneath. So again, I drew some arbitrary rectangle. First, I'm gonna name it ground. Okay, I'm gonna give it a slightly different color. I'm gonna make it a little more transparent. And then I'm basically gonna change the dimensions where I go to create rectangle. And again, I want it to be the same size as my substrate because that's really what your ground plane can be as large as you want in theory. However, usually it is the same size of the substrate. It's convenient for manufacturing. And again, it's going to be the same size. So it's going to be -5, -4.5, and then it's going to be in the Z, 0 for Z. So it's going to be exactly beneath the substrate. Okay. So there we have it. We have a ground plane right here. Well, we have the box, the substrate, and then we have the ground plane. I forgot to change the size. So I fixed the position, but I forgot to change the size. So this obviously needs to be the same size, which is 10 by 9. Okay. Now it should be the same size. Okay. So as you see, because it's transparent, we have the substrate, and then right beneath it, we have this ground plane. Okay. Okay, so now it says unassigned, like here I gave it a material, my ground plane, it says it's unassigned. So I'm just gonna go ahead right now and give it an excitation, or I'm sorry, a boundary. I'm gonna give it a perfect E. So basically I'm telling it, hey, this is a perfectly electric conducting surface. And that's basically gonna be the ground plane. So now this is a perfect E, this is a dielectric, so everything's well defined. Last time we went ahead and defined the boundaries towards the end and the excitations. This time we're going to do it step by step, just kind of show you that it doesn't really matter as long as that towards the end you have every element of your antenna well designed. So now I'm going to go ahead, before I create the patch, I'm going to go ahead and create a hole for my coax feed to go in. Okay, so I'm going to go and create a cylinder, or actually I'm just going to create a circle. And again, I'm just going to draw it arbitrarily. And I'm going to choose, so here I'm going to call it hole. Make it not hard to miss. I want to see where it is. Okay. And I'm going to change the dimensions. Well, first I'm going to position it somewhere closer to the center, such that it is feeding my antenna. And then it's going to have a radius of 0.16. And this 0.16 is pretty much going to be the radius of my coax. So if we go back to that Google image, this guy, this hole right here, where this pin is going to be going through, that's going to be based on that. So you can look up, like in this case, like for example, we're using SMA, you can look up different kinds of connectors. So that's what determines that radius value. So now I see that I have my, if I click on it, I have my hole in here. Oh, and so what I'm really doing is I'm creating the hole in the ground plane because I want to have the coax connect directly, right? Because as of now, the ground plane is acting as a blocker. So there's no way for my cable to go through. So I'm creating the hole in the ground plane. So what I'm going to do is I'm going to go click, I'm going to select this circle. I'm going to select my perfect E. I'm going to go to modular. I'm going to go to Boolean, or I'm just going to select the circle, go modular, Boolean, and oh, it's not letting me subtract. Maybe I need to pick the hole itself. And I go to Boolean, and I go to, why is it not letting me subtract it? Here, one second. Modular, Boolean. Okay, there you go. You have to select both of them. So you can click on the circle and then you can hold your control button and then you select the ground. That way you're selecting both. And then now that I have both selected, I want to tell it, hey, based on that, can you subtract? Obviously, this is a Boolean function, which means there's two things involved. So I'm going to subtract the hole out of the ground plane. So I'm going to actually take the ground, put it in the blank, and I'm going to take the hole and put it in the tool. Okay. That's what basically I'm doing is I'm saying this minus this. So the ground minus the hole. When I click OK, bam, I have my hole in here. Okay. So that takes care of the hole. Does anyone have issues with that? pretty straightforward. So again, you want to select both surfaces. You want to go to modular, Boolean, subtract the hole. And basically what we have created, we created a hole in our ground plane that would allow our coax feed to go in. Okay, so I'm going to go back to my isometric view and I'm going to move things around. Okay, so now I created a hole. Now let me create the actual patch. So again, this patch dimensions, you can get it from calculator based on the frequency you're interested in, based on the material, the dielectric and all that cool stuff we talked about last time. So I'm just going to create a rectangle. And again, I'm going to place it arbitrarily. I'm going to first name it. So this is going to be my actual patch. I'm going to give it like a very bright red color so we don't miss it. I'm going to make it only slightly transparent. Okay. All right, so that takes care of the patch. Now, obviously, it's not where we need it to be. It's not. It should be placed on top of this hole. Otherwise, this feed would not be going to it. So I'm going to move it around, and I'm going to give it a placement of -2, -1.5, oh, -1.5, and then because I want the patch to sit on top of the substrate, not on the ground, I'm going to give it the height that I gave to the substrate. Okay, so in this case, it's going to be 0.32 for the z-axis. So that would take care of the position. Okay, now obviously I need to change the size. So I'm going to go and change the size. And in this case, my x-axis and my y-axis, I'm going to give them dimensions of 4 centimeters for x and then 3 centimeters for y. Okay, now if I notice, that has taken my patch and it put it right on top of the feed. Okay, so right now we have a ground plane, we have a substrate, we have a hole, and we have a patch. Okay, but still, as of now, there's nothing connecting the ground plane. There's nothing really in between the patch itself and the ground plane, right? So right now we have the different components, but we don't really have anything that can excite the antenna. So now we designed and implemented all, our parts. We want to go ahead and start working on the coax cable. Now we went ahead and created a hole for it. So now first, let's create this part of the cable, which feeds into the bottom, basically, or the ground plane. So I'm going to go ahead and create my coax pin, and I'm going to create a cylinder. And again, you could in theory go there and extrude it and pull it back, but I'm just going to place it somewhere arbitrary to show you how you can adjust the dimensions completely in the position. So again, this one, we're going to call it coax. Okay. And for this one, I will move around the dimensions. Now, because my hole was around -0.500, this has to be centered exactly where that hole is going to be. So the center position is going to be -5, 0, 0. And then basically what I have to give it is I have to give it a radius and a height. Now the radius, as we established, was 0.16. That's basically the radius of the hole that we're able to drill. And for the height, I actually want it to go down. So because this is starting at the base, at the ground plane, in this case, my connector is actually even beneath that. So I'm going to make it go down even further. So in this case, I'm going to give it a height of minus, let's say 0.5. In this case, doesn't really matter. So this is basically your coax going into where that hole was placed, okay? Now, obviously, this is the dielectric part. We still need to create the conductive part that eventually would tap into the patch antenna. But if I were to view it like, let's say, the top view, the front view, so we have the coax, the dielectric, and then the patch on top, okay? But still, as of now, sure, we have this connecting, we still don't have our patch connecting to the inner feed of the coax. So what we need to go ahead and create is we need to create the actual metal part of the coax. So if you look inside a coax cable, you have the actual central core, which is dielectric, but then you have an insulator, and then sure, you have like a shield on the outside that prevents it from leaking. But the key idea is you have a center metal core surrounded by a dielectric, which is exactly what, so we created the dielectric part. Now we need to go ahead and create the metal part. So the metal part obviously needs to be a bit thinner. So again, I'm going to go to my isometric view and I'm going to create a cylinder. Again, I'm going to place it somewhere arbitrary because I know where I want to place it. I'm going to rename this and I'm going to name it coax spin, for example, or you can call it like coax conductor. Now this is going to be a perfect electric conductor. So I'm going to change the material to PEC, or again, you could use like aluminum or whatever material you're interested in. Now I'm going to make this red also because my patch is red. I'm going to make it a color closer to red. So I know that this is conducting, and I'm going to hit apply. Obviously, it's not what I want it to look like, but I can easily go ahead and change that. So I want it again to be where my hole is, and I want it to be where my waveguide is. So the position for that is -0.5, 0, 0. Okay. I want it to go through along the z-axis. Now the radius for the dielectric part for the whole hole was 0.16. Now, obviously, we don't want the metal part to be also 0.16 because then basically there will be no dielectric left. So what we want is we want it to be like roughly half that amount. So if you look here, this is kind of like exactly in the center, and it's eating up basically half of that radius. So I'm going to give it 0.07. Okay. And then my height, I want it to penetrate through that same dielectric cylinder that I drew through. So in this case, it is also the height of 0.5, right? Because I want it to go beneath the ground plane. So then when we click on that, we see that, okay, now we have our conductive part of the cylinder, and we know that this is a PEC, so it's a metal. This guy is not, in this case, it's a vacuum. I mean, you probably want to change it to like, again, something like a, like whatever type of dielectric material is used for a coax cable. And again, you would go here and click material. Vacuum itself, in this case, is good. So let me just check. Yeah, so this looks about right. Now, there's one more issue in that we have a coax, we have the metal pin and everything, we have a ground plane, we have substrate, but our patch is not connected to our pin right here, right? So we want to fix that. So we're going to create one more cylinder, and this cylinder this time is going to penetrate through the actual substrate itself. So if you notice, if I go to the front view, everything, all the cylinders we have done so far, all two of them, have basically been beneath the ground plane, right? Because again, the goal is we were trying to make this probe patch antenna, which looks something like this, right? So we're still beneath the ground plane. Now we need to go ahead and create this guy, this orange guy, which is connecting the patch into the actual conductive part of the coax. So we're going to go ahead and create one more cylinder. I'm going to go back to my isometric view, which is kind of my baseline. I always like to go back to that because it's neat. And then again, I'm going to go choose cylinder in arbitrary position. I'm going to name it probe, as in the piece of metal that's penetrating through the substrate. And I'm going to give it a perfect electric conductor because we want it to conduct electricity. And I'm going to also give it the color red, or again, something similar to red that I can know this is conducting. Okay, I'm going to make it a little transparent. So now if we take a look, we have, well, it's not, so we have this probe right here. We click on it. Oh, I did not. It's oh my god. This is funny. So what have I forgotten to do? It's still right here, right? So I gave it a material and I told it what it's gonna serve, but I still obviously need to go tell it where to go. So I need to go and click on create cylinder. So again, remember, there's this gray box and the yellow cylinder, or the yellow geometric shape. The gray one is always going to take care of the name, the material, what purpose it is. The yellow is always going to take care of geometry. What does it look like, where it's positioned? Okay, so I'm going to go to create cylinder, and I know that my hole, my coax, my everything is centered around minus 0.5, 0, 0. So if I do that alone, I know that's going to take it exactly where I need it to be. Now I need to make it a bit thinner such that it's able to match exactly the conducting piece going through the coax. So keep in mind, do you remember this little piece of metal that we put through the coax? That needs to basically connect with that. They need to be the exact, they should look the same, because that's essentially what you're doing. When you're putting the probe in, you're peeling out that dielectric piece and you're letting the conductive part penetrate through that substrate. So I'm going to give it also, so we know the position for it. I'm going to make the radius the same as my conductive part of the coax. And I'm going to, again, want it to go through the substrate. So that's going to be 0.32. Okay. So I believe this should be good. Yeah. So as we can see, now we have this part, which is going through a coax, extending into this part, which is going through the substrate. And then eventually all this is going towards the actual patch itself. Okay, so these are our 3 pieces of conductive surfaces. Okay, so again, your signal. So what you would imagine is this coax now would, so this is like inside the CubeSat, while this is kind of like, think of it as the wall of the CubeSat, and the patch antenna is outside the CubeSat. And on this side, you would have this coax connecting you back to your actual radio. So your hardware, your electronics, whatnot. Okay, cool. So now, before we start simulating, we want to make sure everything is good. So we have our substrate, we have our ground plane, we have our patch antenna, we have drilled a hole, and we fed the cylinder through this hole. We made the coax, we made the probe feed, and we made the conductive part of the coax. So I think everything looks good. Now, we want to make sure we've assigned everything. So we did assign a perfect E surface to the ground. We did give a material to each thing involved. Only thing that is unassigned is the patch. So we're just going to make the patch also a perfect E. Because it's a surface. Now, in theory, you could just say it's a metal. Doesn't really matter, but we're going to make it a perfect E, because PEC, because it's perfect electric conductive surface, is going to behave the same way. Okay. Now, the final step is before I tell it, hey, start radiating, I need to give it some boundaries to radiate, right? So if you remember last time when we made the monopole antenna, towards the very end, we created something called an airbox. And that airbox is basically us telling ANSYS, hey, I want you to solve Maxwell's equations between these walls. And based on that, tell me what the radiation pattern looks like. So I'm going to go ahead and create that box. And again, I'm going to place it arbitrarily. So the box, I want it to be the size of the whole substrate in the ground plane. So I'm going to go back to my ground plane and substrate dimensions. First, I'm going to call it airbox. Now, airbox is a vacuum. I'm going to make it extremely transparent such that I know what's going on. I'm going to give it like a black color. So it's going to look a little grayish. Okay, so now I'm going to take this guy and I'm going to give him some dimensions. Now I'm going to give him the same dimensions that I gave for the ground plane and the substrate. Okay. And so this is where I want my box to be positioned. And then I want to give it X size of 10, Y size of 9, and then a Z size of 0. Okay, so I was going to make it level with the ground. So when I look at this airbox right here, so I need to actually, no, I need to give it a Z size that's going to make it higher up. So the Z position I'm giving it is a 0. But I need to give it some height, right? Otherwise, it would not be a rectangle. As of now, it's just it would not be a box. It's just a rectangle. So let's say I give it like 2.32. Okay, so something like that. Okay, so basically what I'm telling ANSYS is, hey, show me the radiation inside this Airbox. Okay. Yeah. So okay. So the way you do it, you right click, you click measure face. Okay. You hold the control button. So you go 1, 2, 3, 4, and the top is 5. And then you right click and you go to assign boundary, and then you tell it this is my radiation boundary. Okay. Rad 1. Sure. That's what I'm going to call it. All right. So now I believe we have everything. So we have, oh, there's one thing we actually forgot. We forgot to create a port. So we created the geometry of the coax, but we didn't tell ANSYS to actually send some signal through there. So I'm just going to draw a circle that's going to go there. So I'm going to, again, choose an arbitrary circle. I'm going to call this my port. Okay. And again, the port is basically how you tell ANSYS to feed an electric current or a wave through something. And so that's my port. I'm going to go create a circle. I want it to be positioned where my coax is, which is 5, 0, 0. And I want it to be, well, actually, I want it to be at the bottom where the coax is. So it's going to be minus 0.5 for the height. So that way it's going to drag it all the way to the beginning of the coax. And then for the radius, I'm going to give it the radius of the entire coax, both the dielectric and the conductive piece. And bam, so I have this circle on the bottom, and I'm going to right click on it, and I'm going to assign excitation, and this is going to be my port. Okay, so I'm going to say this is a wave port, and I'm just going to click next. I'm going to click finish. Okay, so again, you draw the circle. Once you draw the circle, you right click on here and you assign it a boundary. I'm sorry, you assign it an excitation, and then you go to port and you give it a wave port. Okay, so now we have told ANSYS, hey, the circle right here is where I want you to geometrically start pushing these waves into my coax, which I have just defined. So I think, so instead of me saying, I think we are done, there's actually one way you can check if you're done, and that is if you go to simulation and you click on validate. So I have everything validated, looking good. My boundaries look good. My 3D model is good. My mesh ANSYS is taking care of them. I defined a radiation pattern, not pattern. I defined a radiation geometry. The only problem is I have no analysis set up. I haven't told ANSYS what type of simulation I'm exactly interested in. So if you remember, we go here to the project manager, we click on this plus sign, and we see that there's this analysis tab. Okay, so we're going to add a solution setup. We're going to make it advanced so we have more control over what's going on. I don't really care about the name. I think this was like around 2.3 gigahertz. It's probably like 2.35 if I remember correctly. I'm going to give it 20 passes. We're going to click OK. And now I'm going to do a sweep. So I want to actually do a certain bandwidth. I don't want to just do a single frequency. I'm not going to do interpolating. I'm going to do fast, because interpolating is going to calculate between the discrete points that I give it. Fast is going to do an approximation of that. So again, if my central frequency is at like 2.3, and we have very little time, I don't want to run simulations all day, I'm going to make my bandwidth very small. So from 2.2 to like 2.5, let's say, okay, or let's say 2.4, okay, even smaller. I'm going to reduce the number of my points, even less, and I'm going to click OK. Okay, so now let's go back to validate. Now that we've, again, you go to analysis, right click, add solution setup, advanced. You choose a central frequency, and then for the sweep, you choose the range of frequencies, and you choose the number of points that you're interested in doing. So now when we click on validate, it seems as if everything looks good. Everything is ready to go. So we're going to actually go ahead and run the simulation and see whether this antenna that we've built in 40 minutes or less is going to work. So I'm going to click on analyze all. I'm going to save this 2.3 gigahertz patch antenna with probe. Okay, and as I press enter, my simulation starts running, and this screen on the bottom starts showing me my progress, what ANSYS is doing in real time, step by step. So again, it's going through the meshes, solving for specific frequency, and it's iterating, and it's doing all that cool stuff. Should not take longer than a minute because I gave it small bandwidth and I give it smaller number of points, and the frequency is not very high. 2.3 gigahertz it is high, but it's not too high. For example, in my research, when I would run simulations at like 300 gigahertz for horns, that would take some time. So one thing that's common you see in like companies, if you're like doing an internship or like a full-time job in this kind of project, very rarely you will run ANSYS simulations on your local machine. Usually there is some supercomputer cluster that you have access to that's able to run your simulations much faster. For example, me as a PhD student at Northeastern University, we have access to a really good cluster. At all the companies that I'm interning at, each have their own cluster which you can send simulations to, and that just makes life easier. Again, a supercomputer compared to your local machine simply has more processing power and more RAM, so it's able to do the math much faster. Okay, awesome. Well, perfect. As soon as you finish announcing that, I think our simulation is run. We have no more progresses. So we are again interested in looking at two things. One is the S11 parameter, the return loss. But we're also interested in seeing the radiation pattern. So I'm going to go to radiation. I'm going to insert a far field setup, and I'm gonna I'm only interested in this half. So I'm going to start from 0 to 180, and for phi I want it to give me the full range. So that's okay. So I'm going to click on results, right click, and I'm going to go to modal solution data report, rectangular plot, and it's already going to have pre-selected my S11 parameter. And this is basically going to tell me how good of a job I have done in matching my coax cable to my patch antenna, to having the right substrate thickness, to having the right dimensions for everything, such that if it's going to be lossy or not. So if I generate that, I noticed that around 2. So mine was initially designed at 2.3. I'm noticing at like 2.31. The S11 is minus 22, which is really good. If you remember, anything below 10 is generally good. And if you have a lot of power to spare, then you can even go a little bit higher. But when you have a S11 value that is below 10 at the frequency you're interested in, that's not really good. So we see that the S11 is very good, means the antenna is very well designed, very well matched. And this value is in decibels. So this means the loss is very low. So when you have like minus 20 dB, that's the equivalent of 100 times less than like baseline. So if you have here 0 minus 20 dB, that means around here you have more than 100 times less the amount of loss you would experience something around this frequency. So this is how you know that this antenna is well tuned to this frequency. So whenever you think of antenna tuning, especially the central frequency, you want to look at the S11. Okay, all right, now I'm done talking about S11. And you can Google it. You can go on microwave, microwaves101.com. It's my favorite website, one of them. And you can look into return loss or insertion loss. I think if you go to R, return loss, or you can just Google, much easier, return loss, microwaves 101. And here you can read about this, and it probably will talk to you about dB, decibels, how to calculate the decibels and whatnot. So there's the return loss. So you can read a bit more about it. This is, for example, a graph that's showing you return loss, again, in dB versus frequency, which is exactly what we have here. So we have frequency and we have return loss. All right, now the other type of results we were interested in is the radiation pattern. For that, we're interested in the far field. Again, far field as in like, how is my signal going to look like when it's propagating in space, especially at faraway distances? And for that, we're going to choose a 3D polar plot. So 3D, so it's nice for us to visualize. And what we're interested in is gain total, and that's good. So we click on new report and bam. So if this bottom surface is our ground plane over here, that's showing you that the antenna has a gain of 4.5 dB in this direction, okay? So if I picture this as the side of my CubeSat, so this is my CubeSat right here, and this is the patch, the radiation will be coming out of the side directionally, and it will have a gain of 4.5 dB, okay? Now this is very typical for a patch antenna. You probably will have something below like 5 dB, which is still pretty good. Now remember, 3 dB means you're doubling your power. So 4.5, you're more than doubling your power. So this is really good. So if you have like 1 watt at the transmitter, you basically add this amount of antenna gain to that. And then based on where your other satellite is placed, you calculate the loss, the spreading loss, and that tells you how much power you have at the receiver. But this is all simple stuff, at least the geometry. It's a rectangle with a bunch of cylinders and circles, and you're just cutting stuff and connecting stuff together. So that takes care of the CAD aspect. But also really cool about this assignment is the electromagnetics aspect, where you say, hey, this is a metal, this is not a metal. I want this to be my radiation boundary. I want this to be where my signal comes from, the port and whatnot. So it's a really good exercise for you guys to go through. So again, I'm going to put the assignment on Canvas. You have the opportunity to email me all the way till next Friday, to make sure you have all the information you need. And then by the following Friday, you will have to submit both the antenna, the patch antenna and the omnidirectional antenna. And then after that, I think we will move on from antennas and we will start going back to Workbench, and we will start talking about things like heat transfer and fluids, which I'm guessing you guys are taking classes on. So that's probably going to be cool to get to see it in simulation, right? Okay, so again, I hope this was not too bad. Does anyone have any questions? No, pretty good. Everyone's okay. Is anyone panicking, or everyone's relaxed? Okay, cool. All right. So yeah, with that being said, I'm gonna upload this and I'm gonna upload the assignment. So if there's no questions, see you guys next Friday. Okay.